Hi everyone, welcome to section 8.2, Integration by Parts. In this section you will study an important integration technique called integration by parts. This technique can be applied to a wide variety of functions and is particularly useful for integrands involving products of algebraic and transcendental functions. For instance, integration by parts works well with integrals such as integral of x natural log of x dx, integral of x squared ex dx, and integral of e to the x sine x dx. Integration by parts is based on the formula for the derivative of a product. As you can see, d dx of u times v, wherein it's written a little bit differently than what we're familiar with when we first learned it, but u dv dx plus v du dx. And more kind of familiar to you just below, you see u v prime plus v u prime, where both u and v are differentiable functions of x. When u prime and v prime are continuous, you can integrate both sides of the equation to obtain the following. So you have uv equals integral of uv prime dx plus the integral of v u prime dx. So the first integral you see and the second integral, wherein if you simplify, it also equals the integral of u dv plus the integral of v du. By rewriting this equation, you obtain the next theorem. So integration by parts. If u and v are functions of x and have continuous derivatives, then the integral of u dv is equal to u times v minus the integral of v du. Now it looks pretty complicated, but it actually works out well. Anytime you have an integral that can't be integrated in other or using other approaches that we've seen in the past. The formula expresses the original integral in terms of another integral. Depending upon the choices of u and dv, it may be easier to evaluate the second integral than the original one. Because the choices of u and dv are critical in the integration by parts process, the guidelines below are provided. So there's only two, but I would certainly pay attention to these as you continue. Try letting dv be the most complicated portion of the integrand that fits a basic integration rule. Then u will be the remaining factor or factors of the integrand. Second, try letting u be the portion of the integrand whose derivative is a function simpler than u. Then dv will be the remaining factor or factors of the integrand. Note that dv always includes the dx of the original integrand. Okay, and we'll talk more about the context of why that particular expression needs to be applied in the theorem up above. And you're going to see that pretty nicely unfold in some of the examples we're about to dig into pretty quickly. When using integration by parts, note that you can first choose dv or first choose u. After you choose, however, the choice of the other factor is determined. It must be the remaining portion of the integrand. Also, note that dv must contain the differential dx of the original integral. All right, example one. As you can see, I've already performed all the work for this, so I'm going to walk you through it. So for example one, find the integral of x e to the x dx. So our goal should be to set this up where we have essentially the integral of u dv. And the reason that is, according to the integration by parts theorem from the prior page, here's the setup. If the integral of u dv is what we were kind of shooting for or what we have, it will be as easy as rewriting it as u times v. You have to establish u and v, of course, and you can solve for each if you have the other, minus the integral of v du. I'll explain as we continue here. So again, we have a goal, and we know where we're kind of going towards in the end, generally speaking. So I have 4 different choices here for us to take a look at. Based upon the original problem, if we were to call u x and dv, then the remaining portion, that's an option. Okay, keep in mind when you're doing this though, you are going to have to split things up accordingly. You're going to have to do all the necessary work to find du. If you essentially call that u, that would be your du. There's your u also in the context of the general theorem. dv kind of working backwards, well, you can come up with v here as well as v there. dv in particular, that whole quantity we can kind of work with if you think about just integrating to get v. The second choice, which is actually not going to work, is if we were to call u e to the x, therefore dv would be x dx. Option 3 would be to call u maybe just 1, while the remaining portion x e to the x dx would be dv. Or lastly, you can attempt taking the integral of x e to the x dx, where u is that quantity you see in parentheses, and then dv is what remains. So we're going to stick with option 1, and I'll explain how it all unfolds in a moment. So u equals x, and dv equals e to the x dx. The guidelines suggest the first option, because the derivative of u equals x is simpler than x, and dv equals e to the x dx is the most complicated portion of the integrand that fits a basic integration formula. Okay, so if, again, dv is equal to now e to the x dx, which is more complicated than certainly the other portion, is the most complicated portion of the integrand. We can go through integrating both sides, as you see here in the next step. So if I integrate the left side and the right side, we're going to be able to come up with v. Clearly, if you were to take the integral of dv, that's just v. And then the integral of e to the x dx, that's just simply e to the x. So we're now establishing right off the bat that v is equal to this quantity, e to the x. We also assigned u equal to x, so that if we were to find du, that's just, well, dx. Moving on. According to, again, what our goal kind of theorem is to set it up into, the integral of u dv is equal to u times v minus the integral of v du. U times v, well, remember, u is x, so there it is. And v now is e to the x, so there's that. X e to the x minus integral of v du. Okay, so we know what v is. Okay, again, e to the x. We also know what du is. It's dx. We're going to be able to integrate this. And this is where, again, why we chose the first kind of setup leads nicely to this particular piece being something we can integrate. Okay, and it unfolds great because the integral of just that quantity is simply e to the x. Final answer, x e to the x minus e to the x plus c. And to check, if you want, you could even differentiate your final answer, which we've done in the past as well on other types of integral problems, to see that you obtain the original integrand. And you will if you double check. Example 2. So moving on, and we're going to go ahead and, let's see, push it down all the way here, I think. So find the integral of x squared natural log x dx. Again, we're going to be doing this by parts. I went ahead and assigned u as natural log of x, while dv is x squared dx. If we let dv equal that, and we let u equal that, we're going to be able to, like we did in the last problem, integrate this quantity, which is quite nice, in that if you do that, you get v equal to, again, the integral of this right side ends up being, using power rule, x cubed over 3. If I call u equal to natural log of x, then that means that du is equal to 1 over x dx. So let's put it together again. Here's the goal that we're kind of striving for, kind of generally speaking, u times v minus the integral of v du. So u, natural log x, v, x cubed over 3. If we did not choose u and dv in that particular manner, these would not be manageable, if even possible, nor would the second piece more specifically. And you're going to see on most problems, if not all problems actually, that second part, the integral of v du, won't be plausible if you don't choose the appropriate value, or expression, I should say, for u and dv. Nonetheless, we can now substitute what we said was v. V is x cubed over 3. And we know also du as 1 over x dx. This is something we know how to integrate. X cubed divided by x is just x squared. I can actually also factor out the third. And that then leads nicely to something I can, again, integrate by power rule. Going back to the first part though, natural log of x times x cubed over 3, I can actually just manipulate a bit where I can just move x cubed over 3 out in front and then multiply that by natural log of x. I don't have to do that, but it's a little bit cleaner looking. The second part here, the integral of which I know I can again find by using the power rule. I do that, and that's what, x cubed over 3. The 1/3 is still out in front, but we need to multiply that in the next step so that you have this expression simplified as such: x cubed over 3 natural log of x minus x cubed over 9, and then of course plus c. One surprising application of integration by parts involves integrands consisting of single terms, such as the integral of natural log of x dx or the integral of arc sine of x dx. In these cases, try letting dv equal dx as shown in the next example. Example 3. So as we take a look, we have an integral, of course, but this is a definite integral with a lower and upper bound of 0 and 1. So evaluate from 0 to 1 the integral of arc sine of x dx. So if you call arc sine of x your u, and you call dx your dv, which I also note below, dv is equal to dx, u is equal to arc sine x. We can go ahead and manipulate yet again in such a way where we integrate both sides of this equation. So v now simply is equal to the integral of dx. And that's easy, that's x, of course. U is equal to arc sine of x, wherein that derivative, du, according to a formula we learned way back when, 1 over the square root of 1 minus x squared dx. Let's put it together in the appropriate context. This will be the key step again, of which once you put it into the context of the integral, integrating by parts, using that theorem specifically, you'll find that you'll know whether or not you're right if this integral is something you can't proceed with. Let's take a look. So u times v, arc sine x, times x, there's u times v, minus, okay, so I do have a negative half as well as a negative 2, which speaks to the fact that this is a particular u substitution aspect that I have to take a look at. Another u substitution aspect of which I said u sub 1 is equal to 1 minus x squared, just the radicand. That particular derivative du sub 1 is simply then negative 2x dx. Because the numerator isn't completely the derivative of the denominator, if I multiply by negative 2, but also outside the integral by negative 1/2, which we've done so many times now, this is something we can integrate as such. So it becomes then in the next step, the integral of u to the negative 1/2. Again, we're now replacing the numerator with this u, okay? Technically, we're replacing it and moving up to the numerator, replacing the denominator, I should say. So anyways, so this whole denominator, right, is u to the 1/2, but if we move it up to the numerator, it becomes u to the negative 1/2. And don't forget your du. The minus negative 1/2 of the next step becomes positive 1/2 outside the integral. And then it's just a matter of power rule again. So x arc sine x plus the integral of u to the negative 1/2 is u to the 1/2 over 1/2. The 1/2 divided by 1/2 nicely divide out. And then you're left with, and this looks like my my equal sign kind of covered up my x, but equals x arc sine of x plus, we've got this now replaced with 1 minus x squared. So we've got 1 minus x squared to the 1/2 plus c. Now recall, this whole problem wasn't just about finding the integral, it was also evaluating it. So it wasn't an indefinite, it was a definite integral, correct? So if we plug in 1, here's again our expression, right? We plug in 1 in for x, and then subtract after plugging in 0. The answer to this particular area, which is what it is, here's your graph. The area under the curve is approximately 0.571. Some integrals require repeated use of the integration by parts formula. Example 4, we will talk about in another video and or an audio version. And that should cover, for today at least, part 1.